Okay. So, Chapter 6. We're going to be getting back into math for Chapter 6. So, buckle up. Things are going to get a little bit more challenging for some of you. So, first, I want to give you a reminder about molar mass. So, ionic compounds don't have molecules, but covalent... What the heck is going on here? I tried to open that about 5 or 10 minutes ago. I am upset. Okay, so let's go back here. So, ionic compounds don't have molecules. Covalent compounds do. So, the molar mass is the mass of 1 mole of a substance. The molecular mass is 1 mole of a molecular substance. And the formula mass is the mass of 1 mole of an ionic substance. Okay. So, we can use molar mass for anything. Molecular mass technically is only for covalent compounds. Formula mass, that could be for ionic or covalent compounds. Okay. Whatever. But regardless, they all work pretty much the same way. The molar mass is the mass in grams equal to the mass in atomic mass units of one atom, molecule, or formula unit of the substance. So, first up we have sodium phosphate, Na3PO4. Let me hop over to the periodic table. And here's sodium, the mass of an atomic mass of 22.99. Come on, there we go. So there's 3 of those, so we multiply that by 3. Phosphorus, likewise, over here, 30.974. There's 1 of those. And then we have 4 oxygens, and each oxygen is 15.999. So 3 times the mass of sodium, 1 times the mass of phosphorus, 4 times the mass of oxygen. We add all those together, we get 163.04 grams per mole. That's the molar mass of sodium phosphate. Here we have ethanol, C2H5OH. There are 2 carbons, there are a total of 6 hydrogens, even though it's written a little funny, and then 1 oxygen. So we multiply 2 times the mass of carbon, 6 times the mass of hydrogen, 1 times the mass of oxygen. We add that all together, we get 46.068 grams per mole. Then we have gold, 196.97 grams per mole. It is just the number that comes right off the periodic table. So that's how you find molar masses. And reminder, all roads lead to mole. Okay, we work in mass in the lab. Stop that. We work in mass in the lab because that's what we can measure easily with a balance. Particles are the things that actually do stuff when you have chemical reactions going on. Moles are the happy medium. Okay? Moles have the same ratios that you get with particles. 2 molecules of hydrogen react with 1 molecule of oxygen to make 2 molecules of water. 2 moles of hydrogen react with 1 mole of oxygen to get 2 moles of water. So they have that same ratio, but they aren't the ridiculously huge numbers that you get with particles. Okay? Because atoms, molecules, those things are incredibly ridiculously small. So moles are the happy medium. They have that ratio, and they have the same sort of size as mass does. The conversion between mass and moles is using the formula mass or molar mass. And the conversion factor between moles and particles is Avogadro's number. Now, we will very rarely have to go to particles. That's not really a thing we do. But we go between mass and moles all the time. And later on, as we start dealing with solutions and gases, we're going to find other ways to convert between things we can measure in the lab and moles. So, the math part of chemistry is coming back in. So remember how I said you needed to get good at molar masses? This is where that's coming. Yeah. Okay. So if you had trouble with those before, practice it some more. Practice right now. Go and practice. Get good at this right now, because you cannot succeed on this coming test on Chapter 6 if you do not get good at Chapter 6, at molar masses. All right, so a little bit of practice. How many formula units are there in 10.524 grams of solid sodium hypochlorite? Sodium hypochlorite is bleach. Okay, so sodium hypochlorite. Let's bring up this guy. All right. Sodium hypochlorite. Hopefully you remember from your ionic compounds, hypochlorite is ClO1-. So sodium hypochlorite would be NaClO, but it's usually actually written as NaOCl. I'm not too sure why when we're talking about bleach, but whatever, NaClO. So 22.990 for the sodium, plus 35.450 for the chlorine, plus 15.999 for oxygen. 9, 3, 4, 4, 7. Gives us a molar mass of 74.439 grams per mole for the sodium hypochlorite. Now, what I asked for was the number of formula units. Formula units are what we use for ionic compounds instead of molecules. So sodium hypochlorite is an ionic compound, so it doesn't have a molecule, but we can pretend it sort of does. In all ways, it will function exactly as a molecule would. I just like to be pointlessly pedantic about it in order to make sure that you remember that ionic compounds don't actually have molecules. So that means I'm asking for particles. So we're going to have to convert from mass to moles, then from moles to particles for this problem. Specifically, I said 10.524 grams of solid sodium hypochlorite. So 10.524 grams times where you're going to goes on top. We're converting to moles from grams. Okay? So we already have our grams per mole, so 74.439. This is the same. We're dividing by the molar mass. Okay? So this will give us our moles of sodium hypochlorite. So I've opened up the calculator. 10.524 divided by 74.439 gives us 0.14138 moles of sodium hypochlorite. All right. From there, we can convert to particles, formula units, by multiplying by Avogadro's number. Because Avogadro's number is 6.022 times 10 to the 23rd per mole. Okay. So it could be molecules per mole or atoms per mole, or, as in this case, formula units per mole. Okay. So now the moles will cancel, and that will leave us with just formula units. So now, back to the calculator, multiplied by 6.022 times 10 to the 23rd, and that gives us 8.514 times 10 to the 22nd formula units of sodium hypochlorite. Oh, 453. So my answer is going to be very slightly different. Not by much, though. All right. So this is how you do that sort of problem. Okay, remember, molar mass gets you between mass and moles. Avogadro's number takes you between moles and particles. All right, so now let's go ahead and carry on with the real start of Chapter 6, Chemical Equations. This is where we are going to start getting into the stuff that really looks like chemistry for most people. Okay, chemical equations. We're going to do some reading of chemical equations. Chemical equations are sort of like a sentence, and we're going to go over some vocab and what these things represent and how we can read them. So first off, on the left-hand side of your equation, you have the reactants. Reactants are the things that you start with. They combine together or they decompose, whatever. They're what you start with, and they will undergo the chemical reaction in order to make the stuff on the other side, the products. That's what's being produced. Okay. That's what you'll end up with when you're done. The arrow in the middle, if you were to read this as a sentence from left to right, it just means yield or yields. The reactants yield the products. Okay. So it's not like an equal sign in math, okay, because you're transforming this into this. We're not saying that they are equivalent. It's a transformation. All right. The subscripts represent how many atoms there are of each element in that particular molecule. When you are balancing equations, you never, ever, ever touch the subscripts. Not even a little bit. Not at all. If you change the subscript, you change it to a different substance. If you go from O2 to O3, you've transformed it from oxygen, which you need for life, to ozone, which you can use to sterilize water. Okay, so don't never, ever change the subscripts. The things in parentheses represent the physical states of the compounds. Sometimes this is very important, sometimes it is less important. I usually try to remember to include those when I'm being careful. Sometimes I leave them off because, like I said, it doesn't always matter. Sometimes it does matter a heck of a lot, sometimes it doesn't. So S means solid, G means gas, and L means liquid. Later on, we'll encounter AQ, which means aqueous, which means dissolved in water. The coefficients are the numbers in front. Those tell you how many molecules or formula units or atoms you have of that particular substance. So for this reaction, we have 1 molecule of glucose reacting with 6 molecules of oxygen to produce 6 molecules of CO2 and 6 molecules of water. Okay. When you're balancing the reaction, you do fiddle around with the coefficients. You don't touch the subscripts, you do change the coefficients. Now, sometimes we include more information above and below the arrow. This can be things like the Greek letter delta means that we apply heat to the reaction. We could put something like H2SO4. That means it takes place in acid. That usually means that acid catalyzes the reaction. We could put a specific temperature. Rather than just saying apply heat, we could say that it has to take place at a certain temperature. Or we could say it takes place like under an argon atmosphere. We're saying that this particular reaction, some of these components are very sensitive to oxygen, so we put it under an argon atmosphere. We can say what pressure something has to take place at. We can put a whole lot of information, any information, all of our information, above and below the arrow. Sometimes we don't bother because our reaction isn't that specific. So for example, this one, we're just looking at burning sugar, or the thing where you get energy to live. Metabolize. We're metabolizing sugar, right? We don't really need that extra information. So that is how you read a chemical reaction. Pretty simple, pretty straightforward. Reactants on the left, products on the right. Don't touch the coefficients, don't touch the subscripts. Do play around with the coefficients. There we go. So now, this is the part where it's going to start getting a bit tricky. Balancing chemical equations. People have a little bit more trouble with this. So, I told you once upon a time, conservation of matter would be important. Okay. Conservation, if something is conserved, that means that whatever you start with, you end with. Whatever you end with, you started with. Okay. Nothing disappears, nothing appears. There's no magic. So this is where you're going to have to start keeping track of individual atoms. Okay. So when you are balancing a chemical reaction, you just change the coefficients until the numbers match. Okay, until the matter on the left is the same as the matter on the right. That is to say, the total number of atoms of all your stuff is the same. Okay. So now I'm going to go ahead and work through these 3 reactions. All right, so first up, the Haber process, whereby hydrogen and nitrogen are combined to produce ammonia. All right. This one is one of the easier ones to balance. So we have H2 plus N2 yields NH3. Right. When I write these things out, I typically make it a point to leave space so that you can put coefficients in there. All right, so we have hydrogen and nitrogen. Those are the two elements. This, you don't have to do this, but this I find is a really good way of balancing reactions, keeping track of all your atoms as you go along. Okay. So we have 2 atoms of hydrogen on the left and 2 atoms of nitrogen on the left. And on the right, we have 3 atoms of hydrogen and 1 atom of nitrogen. All right. So the first thing I'm going to do is I'm going to go ahead and I'm just going to put a 2 in front of ammonia. Okay. So that 2 will double the number of nitrogens, bringing it to 2. It will also double the number of hydrogens, okay, because we have 2 molecules of ammonia now. So that brings this up to 6. Okay. Now we see that our nitrogens are balanced, but our hydrogens are not. We have 6 hydrogens on the right. We need to get that to balance. And the way we do that is by putting a 3 in front of hydrogen. And then now 3 times 2, we have 6 hydrogens. Okay. So the other rule that we have to obey for our chemical reactions is that the coefficients have to be reduced. Okay. So in this case, we 3, 1, and 2. There's no common denominator. We can't divide all of our coefficients through by any number. But if it was 6, 2, and 4, we could divide them all by 2, and we would have to do that. So it's kind of like ionic compounds in that respect. Remember, ionic compounds, the subscripts have to be reduced. Well, for chemical reactions, the coefficients have to be reduced. Now we're going to burn us some methanol. So we have C3H6O plus O2 yields CO2 plus H2O. So we have carbon, hydrogen, and oxygen are our 3 elements. We have 3 atoms of carbon on the left. We have 6 atoms of hydrogen. Now be careful. We have oxygen in 2 separate molecules here. Okay. So 1 atom of oxygen from this guy, 2 atoms of oxygen from this guy means we have a total of 3. And on the right, we have 1 atom of carbon. We have 2 atoms of hydrogen. And once again, we have 2 atoms of oxygen plus 1 atom of oxygen means 3 atoms of oxygen. So, little bit of advice. Go ahead and save oxygen for the end. When you have something like this. Why? Because oxygen is all by itself here. Okay. For this guy, if you try to change one element, you'll also be changing the other 2. If you try to change carbon, you'll also be changing oxygen. If you try to change hydrogen, you'll also be changing oxygen. But here, oxygen, you can save it for last, and you won't have to worry about changing other elements while you're trying to fix oxygen. So save him for last. All right. So let's go ahead and balance carbon. We need 3 carbons, so we put a 3 in front of CO2. That means that now we have 3 carbons on the right. Now 3 times 2 is 6, plus 1 means we have 7 oxygen on the right. Okay, so once again, you have oxygen between multiple molecules, so you got to be careful to make sure that you're getting all of it. Okay. All right, now we have 6 hydrogen over here, so we're going to put a 3 in front of water. So 3 times 2 is 6 hydrogens, but now we have 6 plus 3 is 9 oxygen on the right. So now we need to balance oxygen. This can be confusing. One thing you can do is just try changing numbers. Or if you're comfortable with algebra, you can say we have 1 oxygen from this, which we're not going to touch. We're just going to leave this thing alone, because if we change the coefficient here, we'll also be changing carbon and hydrogen, which means we'd have to come back through and change those. We don't want to do that. So we're just going to be focusing on this. So we have some number, x, that we want to put in front of oxygen. This gives us 2 atoms of oxygen for every one of those molecules. Plus, we get 1 atom of oxygen from this guy. Okay. And we want that to add up to 9. Which means 2x equals 8, or x equals 4. Which means we want 4 molecules of oxygen over on the left. 4 times 2 is 8, plus 1 is 9. You don't have to do it this way. You don't have to be all mathy about it. You could just try, saying, okay, 3. Well, 3 times 2 is 6, plus 1 is 7. No, how about 4? 4 times 2 is 8, plus 1 is 9. That'll do it. So, remember, always, whatever consistently gets you the right answer is the way that you should do this. That's all that really matters. Okay, consistency, just whatever works for you. Okay. So now let's go ahead and do this last problem. Let's commit a war crime with a bit of phosphorus and oxygen, making diphosphorus pentoxide. All right. So all we have is phosphorus and oxygen. We have 4 atoms of phosphorus and 2 atoms of oxygen. And over on the right, we have 2 atoms of phosphorus and 5 atoms of oxygen. So we're going to go ahead and double this, because that way we get 4 phosphorus. And then 2 times 5, that gives us 10 oxygens. Which means all we need to do now is fix the oxygen on the left. Well, we need 10 of those, so we'll put a 5 in front of that, which gives us 10 oxygen on the left. So some of these problems are really, really easy. Some of them are a little bit more difficult. There will be some classes of combustion problems that are particularly unpleasant. We'll deal with those when we get to them. So here's some more practice. I recommend you go ahead and pause the video now. Try to work through these 3 problems, and then bring it on back when you're ready to see the answers. Okay, so welcome back. I know you didn't pause it. You're a jerk. I get it. So let's go ahead and work through these. First up, we are burning butanes. So C4H10 plus oxygen yields CO2 plus H2O, carbon, hydrogen, oxygen. 4, 10, and 2, 1, 2, 3. Okay, so let's go ahead and get cracking. We need 4 carbons, so we put 4 in front of CO2. It gives us 4 of those. Then 8 plus 1 makes 9 oxygen. Let's see, let's put it up there. Okay, good. That gets rid of the glare. Now let's go ahead and balance hydrogen. We need 10 of those, so 5. 5 times 2 is 10 hydrogen. 8 plus 5 gives us 13 oxygen. All right, like I said, there will be a class of problems that will give you some trouble. There is no number that you can put in front of this that will get you 13 oxygen atoms, right? Because these coefficients have to be whole numbers. So how do we do this? Well, we cheat, sort of. Okay. 2x equals 13, so x equals 13 halves. Okay. If we were allowed to use fractions, then the coefficient in front of oxygen would be 13 halves. We're not allowed to use fractions, but we can use this as a sort of placeholder, because what we do next is we just multiply all of our numbers by 2. So 1 times 2, that becomes 2. 13 halves becomes 13. 4 becomes 8. 5 becomes 10. And that is going to change all of our amounts. 2 times 4 means we now have 8 carbon on the left. 2 times 10 means we now have 20 hydrogen. 13 times 2 means we now have 26 oxygen. And on the right, 8 times 1 gives us 8 carbon. 10 times 2 gives us 20 hydrogen. 8 times 2 is 16. 10 times 1 is 10. 16 plus 10 gives us 26 oxygen on the right. So that is something you can do. If there's no way to get to the answer you want, it's not really cheating to use a fraction, so long as you intend to get rid of the fraction when you're done. So now we look at our coefficients, 2, 13, 8, and 10. There is no number we can divide those by in order to reduce those, so that is the answer to the combustion of butane. Our next problem is the rusting of iron. So we have metallic iron plus oxygen yields rust, Fe2O3. Our only two elements are iron and oxygen. We have one atom of iron on the left. We have 2 atoms of oxygen. On the left, we have 2 atoms of iron and 3 atoms of oxygen. All right. Now, let me let you in on something. The subscript on oxygen over here is 2. So it is always going to be even. Okay. If you have 2 molecules of oxygen, that means 4 atoms. If you have 7 molecules of oxygen, that would be 14 atoms. Okay, so the number of oxygen atoms on the left will always be even. But on the right, that's not the case. We have a subscript of 3 for oxygen. So in order to get this to be even, you have to multiply it by an even number. Okay, so let's go ahead and double that real quick. That'll change iron to 4. And oxygen to 6. That'll make this a little bit more straightforward to balance, because now we just need 4 in front of iron, and then we put a 3 in front of oxygen, and now everything is balanced. 4 atoms of oxygen react with 4 atoms of iron react with 3 molecules of oxygen to produce 2 formula units of iron 3 oxide, or rust. And finally, a reaction that you do not want to attempt at home. Okay, this is the reaction of sodium hypochlorite and ammonia. That is to say, this is one of the reasons why you don't mix bleach and ammonia. There are lots of reactions that happen. This is just one of them. It produces a lot of very nasty gases that are very bad for you, and you do not want to breathe them. So we have sodium, oxygen, chlorine, nitrogen, and hydrogen. So we got a lot to keep track of this time. So we have 1 sodium on the left, 1 oxygen, 1 chlorine, 1 nitrogen, and 3 hydrogen. And then on the right we have 1 nitrogen, 3 chlorine, 1 sodium, 1 oxygen, and 1 hydrogen. Okay, so this one is not going to be anywhere near as bad as you might fear. Okay? I will go ahead and start over here by putting a 3 in front of this guy. Okay? We have 3 chlorine on the left. We have 3 chlorine on the right, so we'll get 3 chlorine this way. So 3 means we now have 3 sodium, 3 oxygen, and 3 chlorines. Now we need, well, let's just go ahead and put a 3 in front of this guy because we need 3 sodiums, so let's see what happens there. That'll give us 3 sodium, 3 oxygen, and 3 hydrogen, and that's all it takes. Okay? You don't always have to see a clear path forward. Just identify one thing you need to fix and fix that. See what else changes, and then, do the next thing. Okay. If you find yourself going round and round in circles, then go ahead, stop, erase your stuff, and start over. And double check your coefficients, or double check your subscripts, because if you just keep going around and around and around, changing numbers and changing numbers and changing numbers, and it just keeps going wild, then you might have written down something wrong. But the possibility exists that you're just focusing on the wrong thing. Try choosing a different starting point, if you do have everything written down correctly, and double check your math. You might have forgotten to add an atom from another thing, like going back up here when you have oxygen in two compounds. If you're not careful, you might forget to add something like that. So there's various ways you can go wrong. But again, this is the sort of thing that you want to practice a lot. Okay? Balancing reactions is very, very important in chemistry. I mean, that should be obvious. Okay, so go ahead and practice, 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 practice. Okay, and as with everything else, there are going to be 5 million web pages if you run out of practice problems in the book. All right, and I'm going to go ahead and end this particular video here, and I will come back in the next video